thank you very much for all of you. We have 2 rooms of people for the keynote, for this welcome and the keynote. So because this room was not enough to welcome all the attendees, so we have prepared the second room, room 5. There are still few seats free here, but maybe somebody is already there. So hello everybody and welcome also in the other room. So first of all, herzlich willkommen. I try with my best Deutsch.
That's all for the Deutsch.
That's all for the Deutsch. To the second edition of Voxxed Days Zurich. We are very happy about this conference. And we would like just to repeat what we explained last year and what is Voxxed Days, because we think we are a little bit different than many other conferences. And Voxxed Days is a network of international conferences happening now all around the world. There will be also Voxxed Days Singapore this year. Voxxed is also a website where many developers write a lot of technical articles and share their knowledge in an open and without advertisement. And it's a community of people, and that's also an important point for us, that we feel and we collaborate each other all together. This is really something important and at an international level. And the second point is that it's really done by developers. So we are not conference organizers, we are not event managers, we are not such an experts. We are trying to do our best, and we hope you are happy with what we have. But we are developers, first of all, and we try to do this for developers. So our main audience and targets are developers. We try with Voxxed to be cross-technology, and so we welcome talks and speeches from many different topics, because today it's normal to speak about polyglottism in the programming world, and all of us often switch from one language or from one framework to another one. What is important in these conferences, and you will see it today, is the content. The content of the talk is what all of us aim to select the best ones so that you all are happy, and that's the point for Voxxed Days. Just to explain you why we think it's important to have a conference driven by developers. So the first point is we all know many developers, and many developers in their free times contribute to open source projects. And this movement and these energies you all, or many of you, spend, we would like to promote and to share this across each other. So also the sharing part is very, very important for us. And then in our case, we try to be Swiss-made. It's like our goal is to promote the Swissness and the competencies we have in Switzerland about development and the software skills that we have here. Another thing that we really love about the developers is that the developers are the people who does and deliver, and we really think this is one of the most important pieces in the software industry. We don't like too many words and plannings, we like to deliver something. Another very important point for us is that not only we are supported by the developers, but we are supported by companies that understand this philosophy, and really we have to thank all those amazing sponsors. They're really doing a lot of efforts to support all of us and to make this conference possible. Well, thank you very much to the sponsors because of that. Thank you.
So yes, about the conference, it's the most important thing of the conference, of course, are the speakers. And I believe we put together a great speaker lineup this year. I shouldn't say that because I'm among them, but except on me, I believe we really put together a great speaker lineup. So I also want to say thank you to the program committee that helped me to choose the talks, and it has been a very long and very hard discussion, because we had lots of great proposal, and we had to give up to some very interesting talks, but time is limited. And I also want to say thank you to all the volunteers that helped us to put together the venue and everything you will enjoy today.
Exactly. Thank you, thank you. Thank you, really. We really need a lot of support during the whole day, and we hope we do it. So what I would like to try to do now is to see if we maintain our promises, what we promised last year, because last year we explicitly mentioned that our first goal is to have fun, to make the developers happy, to have a happy geek. So this day you spend here, obviously you will learn a lot of things for your company, for your work, but it has to be fun. Otherwise it's really just too much and not a little bit boring. From the feedbacks we got last year, we reached the goal, so thank you, and we hope to confirm it. One of the most appreciated things was the beers, and we have the beers again this year at the end of the day. So
3 different kinds of beers.
3 different. The second promise was to make more than 40 sessions. We will not do 40 sessions here in Zurich. What happened is that we have been called by the CERN guys, and this year we will do Voxxed Days Zurich and Voxxed Days CERN in next Saturday. So we are going bigger, but into different locations. That is the way for us to maintain the promise. In fact, what we see now is that Voxxed Days in Switzerland, we are the only country having already 3 Voxxed Days, Mark? We have Ticino since 3 years. Zurich is the second year, and for this year we have CERN. And now in Zurich, this year we have 394 attendees. That is quite a big improvement from last year, and we hope the trend continues. And it means we will have almost or more than 1,000 attendees in Switzerland this year. This is a great thing. The last promise we made last year was DevOps for Kids, to bring also in the German-speaking part of Switzerland DevOps for Kids, and I'm very, very happy to announce that we have it. We are going to organize in Zurich the 26th of August, the first DevOps for Kids in Zurich. And we will do 3 workshops for 60 kids, that's the plan, 10 to 15 years old, so if you have kids in this age, just bring them. We got the support from University of Zurich. They will offer us the location, and everything is already reserved for us. And we got the support of 2 big and important sponsors that we really want to thank. The Swiss Post and Wikimedia Foundation are the main sponsors of this event already, without having organized it yet, but they really trust in us and they gave us the support, and we really would like to thank them for this. So please join the event. It is really, really fun. Thank you. If you want, you can also contribute. So we are still choosing the workshop, so if you have ideas and you want to have fun with kids, just do it, come. If you want to be volunteer during the day, or if your company want to sponsor this event, we will do something better for the kids. So, and everything is no profit and for the kids, so everybody is a volunteer during that day. Yeah? Thank you.
Okay, so some practical stuff. You have the Wi-Fi username and password on your badge, and those sessions will be recorded and will be published online, I believe, next week or within a few days anyway. After Martin's keynote, we will have a quick breakfast, and then we will start with the session. And as promised, we will have the beers at 5:30 in the sponsor area, and there will be a few sponsor giving prizes. And we have a limited number of T-shirts, so if you want your own T-shirt, take it at the end of the conference on the entrance of the venue. Okay. Last thing, please help us to understand what you are enjoying, what you like, what you don't. So tweet with our hashtag, use the mobile app to give feedback to the user. So the name of the mobile app this year is My Voxxed, so look for it and download it both for Android and iOS, or otherwise you're using our voting machine offered by Canoe. Yeah. And that's all. Enjoy.
Let's welcome Martin on stage.
Welcome, Martin. Yeah.
Thank you.
Okay, good morning, everyone. I want to kind of open up here with a question to begin with. Here's an interesting statement. Oops, this is not working. Go back to the old-fashioned way. This question here: a software system can best be designed if testing is interlaced with the design instead of being used after the design. Who do we think said that and when? Is this a recent thing? Is this someone talking about TDD sort of in the last sort of 10, 20 years? Any ideas on which decade? Anyone shout out a decade think this was said? 70s? Good. Any? 60s? Yay, we got some people here thinking the right way. This was 1968 by Alan Perlis. Kind of interesting. I want to go back and look through a little bit of our history, because we forget a lot of our history, and we also think interestingly about, do we do computer science, do we do engineering, what can we do for ourselves? Do people know who Alan Perlis is? People? Anyone heard of the Turing Award? Guess we've got a few people heard of that. Alan is the first recipient of the Turing Award, way back in 1966. In many ways, he's been known as the father of computer science. He'd done a lot of fundamental work on compilers and the first ever parallel programming. So there's some really interesting history in our subject, and many of us don't understand it. We tend to go forward, we tend to hack software, we tend to have a bit of fun with it. We tend to build stuff that looks a bit like this at times. I love collecting interesting pictures of the internet. And so this example, this is Russia. Russia doesn't have a monopoly on this. My own country. There's supposed to be a fuse where that drill bit is. So much for safety. I was down in Australia last year. They're pretty good at it too. So what do we do when we hack every day? Probably a bit of this. So kind of interesting. Are we engineers? Are we software people? Are we just hackers? Are we whatever? But it's kind of interesting how we're looking at some of this. Like, the amount of software we have now in things is getting scary. This is talking about how much software there is inside some of our latest cars. Like 10 times more than you get in a F-22 Raptor, which is the latest fighter we can get. Like way more than there ever was on the space shuttle. In fact, even Mercedes brag about this. They're talking about how they've got 250 times more code in this than there was in the original space shuttle. Like, this is not good. We drive around in these things, and it's kind of scary, because we know what software can do. Like, the new Tesla is now up at 350 million lines of code. Who thinks that's bug-free? I find it terrifying working on any project with more than about 10,000 lines of code. And that's kind of typical. Most people, there's a lot of studies that show that we really, as humans, don't deal very well with code that's more than about 10,000 lines. We just can't fit it in our heads. We can't understand it. We can't deal with it. So we're kind of working this out as we go. Like, another way I look at it is like, how many generations of programmers do we have when you start thinking about it? Like, think about it. How many second-generation programmers do we have? Or even how many third-generation programmers? I can't see in this room, so I'm going to ask people to put up their hands, but I've only met 2 third-generation programmers so far. They were really impressive individuals, and there's something that happens whenever we pass on from generation to generation what we learn. We're kind of very much in the early days of this. We're kind of working it out as we go. Anybody been involved in any of these standards? Like ISO 9001, 2701, capability maturity models. I get involved in a lot of this sort of stuff in the 1990s. I've been writing software for a while now. But so we went from having shit to well-documented shit. That's basically what happened with this. We weren't better at it. We just had a paper trail for it. That's all. We knew how to blame. We get into this blame culture, which is part of the problem as well. I think we need to get better at it, but in a sort of safer, better way. The way I like to think about it is we're kind of living in the era of software alchemy. Like back in sort of the 1600s when we were doing physics, alchemy was a really big thing. Like most people will have heard of Isaac Newton. What many people don't realize is he was one of the biggest alchemists in history. He wanted to turn lead into gold as much as everyone else did, because we're kind of work this out. We're looking for the silver bullet. What are we doing in software? How do we get better? I want to explore the subject of engineering. I'm a computer science degree by background. I spent a lot of time in the engineering department, and I think what we are doing now should be engineering. There's a lot of debate. Is it a craft? Is it a science? Is it engineering? Whatever. But let's explore the history of engineering. Let's see if it fits with us. Let's see if we can learn anything from it. So the history of the term, originally Latin, and we're talking about cleverness or devising things. This is the sort of origin of it. The first example found is back about the 1300s from French, and it's to do with someone who operates an engine. We're talking about a military machine, catapults, things like that. This is where the word engineering comes from, an engineer from that sort of thing. Later on, we introduced the concept of a civil engineer, because a civil engineer was someone who did engineering that wasn't military, because everything was military for a long time. It's one of the sad things of history, but we drive forward technology through war more than any other means there almost is. So let's turn to the source of truth for everything, Wikipedia. Let's see what it says about engineering. Does it fit with how we see the world? Well, engineers must work within constraints. I program Java most days and C++. I feel very constrained. I wish I could have more flexibility to do what I wanted. But let's look at what some of these constraints are. Like, what available resources do we have? Like, I've heard people talk about how they see some people's code and people look like the program like they're a god, where time is infinite, sort of memory's infinite, CPU's infinite. Sorry, it's not. We're constrained. We have to work within those constraints. And those constraints are many forms, not just physical, but imagination and technical. This, I think, is one of the biggest points of engineering, which I think is so applicable to us, is we need to have flexibility for future modifications and additions. The majority of time, and by majority I mean pretty much all of it, we spend time modifying code. Even if you're on a greenfield project, the code that you're writing today is probably modifying the code that you wrote last week. So writing software that's easy to modify, easy to extend, easy to deal with is very much key to doing a good job. And that is engineering at its core. Particularly, we've also got to look at other constraints and ways we're working, and particularly I like this concept of safety. Every other engineering discipline cares about safety and serviceability and dealing with stuff. Like, we need to think about these things too. Like, what does safety mean? So things like memory management, concurrency, all of these things have got serious impacts for safety, and we've got to be able to deal with the safety in a better way. And by understanding these constraints, we can see how we can work, what our limits are, how we can move forward. So I'm starting to like this concept of engineering as an idea. I think it does fit a lot with what we want to do, and maybe we should be inspired a bit by other engineering disciplines. What did Albert Einstein have to say about engineering, since we're here in Switzerland? Is scientists investigate what is already there, but engineers create what has never been. And that is very much what we do. We create this new future The things we're developing in software and how key software is to the world is so much about creating the future in many ways. I remember Alan Kay saying that the best way to predict the future is actually to invent it. We're driving a lot of this forward. So where does software engineering fit into this? So that was engineering in general. Well, the first ever reference to software engineering that can be found is back in this paper, 1967. And the term software engineering was first coined at this point in how we move forward, how we get better. It was popularized by this great woman. This woman is Margaret Hamilton. She led a lot of the development on the Apollo missions, give us amazing things like priority scheduling, sort of testing in certain ways, sort of complete end-to-end testing, human in the loop. A lot of these things all come from her. We don't realize the great work that's been done in our history. I happen to have worked with some people from NASA, and they're amazing, particularly how they focus on safety and correctness and getting it well. A lot of this comes from her. She did some really, really great work in this area. Well, the bulk of what I want to talk about for a second is in 1968, whenever that comment was made by Alan J. Perlis about how we should be doing testing interlaced with the development, came about from this conference that was held in Germany at this point. The idea was NATO got a bunch of their best software people together to discuss how do we get better at this. This software thing is getting really important. How can we do it better? And over 3 days, the great thing about this is it was minuted and it was all captured, and you can read it in this document. It's worth going back and reading this. It's a really, really interesting part of history. But let's pull out a few choice quotes from this. I think it's really good to review that. Look at this. The design process should be an iterative one. Flowchart until you think you understand the problem. Write code until you realize that you don't. Go back, redo the flowchart. Write some more code and iterate till you feel you've got the correct solution. This is iterative development, 1968. Why did it take us so long beating our heads against waterfall when the best people in the world were doing iterative work in the 60s? We don't learn. I think we're not really winning the intelligent ape sort of category at the moment. Look at this. So here's another one. Reliability really is a design issue. You can't add it in. And this is a kind of an example of how many things that we do that are quality of service, like security, performance, reliability, all we call the quality attributes in architecture design, is you have to put them into the requirements. They have to be an upfront concern. You can't add them on later. If anybody's ever tried to add security to a system that it wasn't thought about up front, it's a complete nightmare. I love their point at the end, like, so if you don't do this, you might as well give up. They're kind of pointing out some very interesting things. Here's another great one. The good systems that are presently working were written by small groups. More than 20 programmers working on a project is usually disastrous. Has that changed? 50 years later, I think we're still in the same point. Or how to approach software? Well, let's begin with skeletal coding. Rather than aiming at finished code, the first 46 steps should be aimed at exploring. So interfaces, sizes of critical modules, complexity, adequacy of those modules. Now, some critical items should be checked out. Don't put off the hard stuff to the end. I'm going to come back to that one again. This is one that's sort of been around a lot. Like, how many people have met architects who don't code? I think this is a great example going back to then. It's another interesting concept we could apply that's used in the Air Force to fly. You have to maintain your wings by doing a number of hours per month. If you don't retain your wings. Like this, and should people who are seniors still write a number of lines of code per month? There's a lot of very interesting things about that. I've seen organizations that have debated this and they've turned it around, and now everybody who works within the technical part of a company must write some code, and it does really improve things. I've seen this elsewhere. Whenever Disney was reshaped, one of the things they did is if you don't contribute to the creative process, you don't work there anymore. And it changed it, turned it around. Trying to put in too much bureaucracy, trying to do things with people who don't understand the process is very, very difficult. I think this is really quite funny. It's a bit sad in some ways, but many of the people who design software refer to the users as them. They and them. Like we have the them and us thing. This happens a lot. Most of the designers of software manufacturing think they do it for their own benefit, is what they're pointing out here. Like, so they're doing it for themselves, not for their customer. I've got a simple term for this, is I see so many projects which people are basically doing technical masturbation. They're doing it for themselves, it's self-gratification, it's not for the customer, it's not doing the right thing. And this is actually much more prevalent than we think. We need to be aware of these things and how we deal with them. Right. Estimation is another great example that they showed. So this was from building the first 3 Fortran compilers. This is a really, really capable team. First go they had at it, they were out by a factor of 2. As they built the second generation, this is the same team working with refined practices, doing something that they already knew how to do. They were still overrun. They were overrun by 36% on the second go. And then on the third go, they started getting close to it. So what it shows is that as humans, we're only good at doing estimation for something we've previously done. Unfortunately, an awful lot of software that we write, we have not done that thing before. So it shows you how estimation is really, really difficult to fit into this. So that's the NATO conference. Like, I really recommend you go off and read that paper. It's wonderful and full of gems like that. One of the other people who was at that conference has also done some interesting writing on this, and he's another Turing Award winner, and that's Dijkstra. He also made this point that how we teach computer science has got some serious issues. I've read a lot of Dijkstra's work, and I'm kind of mixed on it. I like some of what he's got to say, and I think some of it's also a bit extreme. Maybe I'm just too liberal with it, and I don't respect his extreme stuff, but there's some very interesting points in it. Like, here's a great paper he wrote on the cruelty of really teaching computer science. In this paper, he pulls out a couple of interesting concepts. One of them is this idea of radical novelty. And I think this is very key. So what we do with computing is so different to most of the things that we do in history. He talks about how you've got to approach radical novelty because it is so different. You've got to have a blank mind. You've got to be consciously refusing to try and link it to anything else. Like, one of the most powerful techniques we have for teaching is sort of metaphor, analogy, and storytelling. We want to relate it to something else. Unfortunately, things that have a radical novelty to them, they feel badly when you compare them to other things because they're so different. And this is where we fall down quite a lot. Like, he gives examples of how if anybody who's ever learned quantum mechanics knows what they're talking about. So if you've studied physics, use quantum mechanics, the radical novelty is so different. So if you go back, things like relativity, quantum mechanics are examples of that. But go forward, things like the atomic bomb or the contraceptive pill, he pointed out, that these things are so radically different and so novel that you actually change the foundations of how people approach things. You can end up changing religion, you can change states, you can change governments, all sorts of stuff, because it is so different. Existing systems don't know how to deal with it. We are now seeing this globally at the moment, whereby our access to information, the internet, how we're using computing, has created a new form of radical novelty that we're wrestling as a people to try and deal with and how we work it out. So how do we work with this? How do we deal with these things that are just so radically novel? And what are the major points to pull out? Dijkstra said there's a few things in it for him. One of them was that anything that's a concept at this level is we got to be able to decompose it. We got to divide and rule, and we got to be able to do decomposition on an unprecedented scale. So we're looking at, if we're going to be great engineers, what are the skills we need to focus on? How do we get better? Well, we got to get better at decomposing these complex problems. If you're working on a vehicle that's got 350 million lines of code, how do we decompose that problem so we can even remotely understand what's going on? So that's one thing to grapple with. The other thing to grapple with is the amplification of changes. Never in human history have we had the case whereby such a small change can have such a big impact. Like, you change a single bit in code and you can cause the entire thing to catastrophically fail. We don't have examples of that elsewhere. It's such a different thing that we have to deal with. So if we look at these as problems, like, how do we learn from this? How do we go forward? Well, I find fundamentally we're all a product of our own experience. So I studied computer science at university, but I also took a few minors as electives, and one of them was behavioral psychology. I think it's a fascinating subject that people really should understand and very applicable to almost most things. And what you learn from a lot of that is that there's a nature and nurture, but fundamentally we're a product of our own experiences. Who we are becomes like what we experience is how we learn, it forms, it shapes who we are. So if we apply some of that thinking, how can we get better? So thinking about how we get better. I've worked with lots of software companies, and I find there's one very uncomfortable truth that you keep finding is we have lots of processes, lots of ways of working, but in most organizations I see, usually the majority of the work that makes the major change is done by one or a very small number of people, often working outside of the process. They're not fitting in with that. What do they do that's different? How do we learn from them? This was something that we were wrestling with back in '68. It was talked about in that NATO conference. So what I want to do is try to break down a little bit of sort of what do some of these individuals do? What do some people do that you observe that do things really well, and what do they focus on? And let's focus on the learning. I want to focus on three things. Like, what should we learn that's applicable in our industry? Where can we learn that, and how do we go about the learning process itself? So let's start off with what should we learn? Get a quick drink of water first. So kind of interestingly, I find algorithms and data structures a fascinating subject. And if you've been following Twitter over the last few days, there's an interesting meme going around about that we don't really need to know so much about algorithms and data structures. That's what the implication is. So DH8 said that the whole thing of going into an interview and on a whiteboard having to write a bubble sort, that's a really good example of how we should badly interview people, because people don't naturally work in that environment. But I think there's a danger here in how people take things too literally and too much of a problem. Like, so are algorithms and data structures a good thing to learn or not to learn? Well, I'd kind of argue there's two ways you can look at them. One is, are you a writer or a designer or creator of algorithms and data structures, or are you a consumer of algorithms and data structures, and are you a good consumer? So knowing what are the available algorithms and data structures that are out there and picking the right ones in your day-to-day job, so you're choosing the right way to represent a relationship, choosing the right way to represent data, is very different from knowing how to write one. It's like knowing about the different types of trees versus writing a new tree from scratch. If you're an engineer in almost any discipline, you know the fundamentals. So if I'm an engineer that's working with buildings and in structural engineering, I know the materials I can apply. I know the compression strength of concrete. I know the torsional strength of steel. I know how wood will behave over time. It doesn't mean I go and make wood or I make concrete, but knowing those things. Now, some people may choose to go off and do the material science and make those things. That's all good as well. Some people choose to do it, not everyone. But if you're going to be an engineer, you need to know how to consume these things. And I'll find that over 25 years of professionally programming and even longer of just writing software for fun, any work I've ever done understanding algorithms and data structures is still applicable. Stuff that I learned about how maps and trees and sorts and all sorts of things that I learned back in the 1980s still apply, and I can use them sort of quite regularly in my job. The fact that I learned to use WebLogic 4.3 back 17 years ago, sorry, that's just gone out the back of my brain and of no use anymore at all. So what is the useful things that we need going forward? I unfortunately corrupted my brain with the early days of EJB, and EJB home and stuff like that still comes and haunts me, the abominations that we created back then. So what is the good stuff? What's the good stuff that we need to learn and we need to keep? So I kind of would argue, spend some time studying algorithms and data structures. There's some great things to learn. Become at least a good consumer of them. But I think what is much more important, which I don't see so much debate about, is design fundamentals. Now, by design fundamentals, what I'm talking about here is understanding coupling, cohesion, separation of concerns, single responsibility principle. These things are so key to writing good software that's maintainable, adaptable, flexible, understandable, so that it decomposes correctly. You don't see people practicing these skills on a daily basis, yet you should be. Like when you look at an API, what are the coupling concerns of that API? How should something be cohesive? You start looking at code and you go, yeah, that's an obvious train wreck, this dot this dot this dot this. It's like doing law of Demeter, tell don't ask. Sort of all those sort of things. Like knowing these things, knowing how to apply them becomes really, really critical. So they just take something like coupling. Who here has heard of connaissance? Very few hands. Connaissance is how we describe coupling in object-oriented design. It's quite a large body of work. It's really interesting. Yet most people don't fundamentally know these things. They probably know the latest thing about Spring Boot or whatever. And sorry, in 3 years' time that won't matter anyway. Yet we don't learn the fundamentals. So if we're going to become engineers, we need to get much better. And we need to get much more precise about these sorts of things. Like if I walk up to a chemist and I say, I'd like you to help me do a titration. People will know exactly what I mean if you're a chemist. If I walk up to someone and say, let's work on this code, it needs to be refactored. Now, that may seem like a simple thing, but you'd be amazed that that statement to some people will mean precisely what it should mean, is that refactoring is a behavioral preserving change, is that the test should still just pass, and you've changed the code to be easier to work with. Through to, I like to use the term refurbishment, is where they'll kind of change quite a bit of it and reshape it, and it will be different. The behavior isn't preserved, it will change, right through to a complete rewrite. But people will use the term refactoring and mean all sorts of things along that scale. We're not very mature yet as an industry dealing with this. So think of the fundamentals. Think about what do we do every day when we start looking at code. Also, let's not get caught in a rut. Think about different programming paradigms. Like I spent the early parts of my career writing a lot of procedural code. I started off in assembly, then I discovered C, and I thought, wow, this is brilliant. Making a function call without all of that overhead of setting it all up myself. It was so nice. And then you discover things like object orientation, and that was great for encapsulation and dealing with polymorphism and different things. It was kind of cool. And then I did that for a really long time. And I noticed that I was uncomfortable with it, and I started doing a lot of things and stealing ideas from Smalltalk and whatnot. And then after a while, someone pointed out to me I was actually pretty much writing functional code. But it's kind of interesting to go study some of these things, and so you go off and you kind of formally learn some of it, and it really helps. Like, learn other paradigms really helps you think differently about a problem. So some of the people I have worked with from NASA, one of the things that they've taught me is approach your testing with a different mindset and a different paradigm than what you're developing the code with. So for example, if you're going to develop code using object orientation, how about approach your test with formal specification? You have to think differently. It's not that formal specification is the best way to do it. It's a different way. Write your tests in an object-oriented way and test functional code. You can do all sorts of really interesting things to think about a problem from different perspectives. It uses different parts of your brain, lets you see the model in interesting ways. And that way we get a deeper understanding of things. So, don't be shy to go and learn stuff. I find the number of people who have put set theory at arm's length for far too long absolutely terrifying. So within object-oriented, we've been using ORMs, which I'll sort of nail my flag up here, I think is an abomination. It's like, there's a database, it's a perfectly good thing, learn how it works and use it correctly. And don't get at it through an ORM, which is just an abomination in a way. It's like entering a three-legged race with two different species trying to run together. Like, get them working together, doing the right things that they know how to do. And as Dijkstra says, we've got to get back to this decomposition and abstraction and think about what it really means. But think about what it truly means for decomposition and abstraction. Like, so decomposed by data, decomposed by function, decomposed by behavior. There's lots of different ways we start looking at that, start dealing with it. And look at what abstraction truly means. Like, whenever we do introduce types, are they really making a concept more precise, more distilled, rather than just putting it in and building a cathedral? If there's one subject I wish I had studied more at school, is mathematics. And I keep finding it is an incredibly useful subject. And I think that the problem that we see is that most people just don't deal with it enough to learn enough from it. And it's kind of fundamental. Like, if you're doing anything with set theory, it's first order predicate calculus. Like, sort of learning what some of these things are, how do we deal with it, we have a deeper understanding. And it doesn't mean you have to go like to really great depths with it, just the fundamentals. So, for example, as we start to go more and more parallel, we're going to hit the problem of we can't go faster, we can't scale up in the same way. So we've got to look at tasks and instructions and work out how do we make them commutative, how do we make them associative. Like these are basic concepts of mathematics, but it allows us to swap orders, that allows us to swap groupings, that lets us get more progress in a parallel sense. Like if you start running off into the Java world using Java streams and you don't understand some of the fundamentals of that, you will not get good throughput. It will not scale up very well. And so you get hit with that. So it's really worthwhile. But kind of one of the key subjects, I think, is communications. We're moving to a very distributed and very concurrent world. So we need to understand good protocols of interaction. So the protocols we have between our little microservices, between our components even we have within a system, how do they interact? Like, does the design fundamentals get respected here of coupling, cohesion, separation of concerns, all of those sort of good things? And the protocols themselves start to really matter. So an example is like, well, what is a protocol? Well, it's not Google protocol buffers. Sorry, that is completely misnamed. And this is another problem we have of our industry. A protocol is not JSON. It is not something like Google protocol buffers. They are codecs. They're a way of encoding and decoding data. A protocol is a series of messages that allows you to have a treatment and etiquette between two different components. So like a protocol for dealing with a file, as a simple example, is you must open a file followed by one or more read and write operations followed by a close operation. That's the protocol with which you deal with something. It starts to become important. And this is not just at a technical level, it's also really important at a human level. Like, we have to work with customers. We've got to understand their domains. We've got to deal with all this. So communication is so key. So if there's one skill to highlight here is communications is probably one of the major things you need to refine and work on every day. Like, be it your interpersonal communication, but also the communication in your software. It reflects things. Like, if you've heard of Conway's laws, like all software takes on the structure of the organization that built it. So if you've got two different compiler teams, you'll get a two-pass compiler, that sort of stuff. If you've got a team that's good at communicating and having good protocols between them, you'll see it reflected in the software as well. So you can almost reverse it in different ways. Like, we're kind of in this interesting world where everyone thinks we're going to build monoliths, and monoliths are shit. Are they really? So if a monolith is shit, so if you can't build a good monolith, so you're going to build a whole pile of microservices. So what happens to shit when you increase the surface area of it? It smells a lot more. So just running to microservices is not the answer. Microservices are great, but drive them from design fundamentals. Like, you're choosing to do it because it's matching some design fundamentals that you want to achieve. So kind of be aware of that. So let's move on from where can we learn? Well, fundamentally, we learn by practice. Kids learn by play. As we turn into adults, why not keep playing? Let's enjoy what we do and practice, but practice the right things. If you're in any sort of discipline where safety is important, you drill. You drill so that under pressure, you do the right sort of things. So every day, we should be thinking about, are our practices enforcing good behavior, or are they enforcing bad behavior? Like, are you being sloppy? Are you ignoring the tests? Are you just letting a red build continue for a long time? What are the practices that we approach to stuff starts to become really important. But so start to consciously practice how we get better. How do we get these things going? Like, so how do we focus on the design fundamentals and do it well? We have to work in teams, and this is a good thing. And that's another great way that people learn is humans are great mimics. We learn from other people. So one of the best things you can do is work in teams with other people you're going to learn from, people you enjoy working from. And so, like, from a career perspective, we should seek out great places to work. One of the great things we have in this industry is we have way more work than we have people who are able to do it. So if you're in a dysfunctional environment or you're not learning, you're not getting anything from it, we can exercise with our own 2 feet and go somewhere that does. We should work in environments where we enjoy it, we get something out of it, or we try to change it and do it for the better. Try to do it in some sort of way, but think about where you'll actively go and work. Like, if you wanted to plan your career, choose where you're going to work is one of the best things you can do for that. You'll start going the right way. And there's one kind of interesting strong point around this, is like I've managed a number of teams. I've been CTO a couple of times in a few firms, and one painful lesson I have learned very, very quickly is that don't work with assholes. It's a really simple thing. Get them out of your team because they're just damaging and dangerous. And like, we'll be shy, we'll be a bit afraid to deal with them. It's much easier to deal with a problem early and deal with it. It's like, people should communicate. Like, we'll go back to that early sort of point is, we got to work, and Conway's law shows us that software will take on the organization of the shape that built it. If you've got a difficult person in the team, you're going to have a difficult piece of software somewhere, and a lot of miserable people dealing with it. So either help them change, or sort of make the team change. And so that you take things forward by you change the team or you change the team. Now, if you're running the team, there's something you can do about it. If you're not in the team, if you're not running the team, you can help influence it from below, or you can ultimately go somewhere else. We can't always get access to all of the people we want to, so how do we learn in other ways? Well, one of the wonderful things we have is lots of great research papers out there that can tell us so much and help us learn from it. So there's been so much said about this. I'm not going to really add to it anymore other than sort of encourage the point. It's just great to go read stuff. Whenever you go into a new area and you don't know it and you can't get information, feel free to go read papers on it. But also read code. I think the open source movement is one of the greatest things we have done for our industry. Because if you're in almost any other discipline, one of the best ways to learn is learn from the work of other people. Like Stephen King was once asked, he's the famous writer, how do you get better at writing books? And his answer was really simple, is read other books, read other good work. By having good software out there that we can read, we can learn from it. And that's what we should do regularly. We should be reading code and reading as much as we can. So read your colleagues' code, do code reviews, do feedback, do them in a really healthy, positive way. Code reviews shouldn't be about sort of anything negative. They're actually a great learning experience for everybody all around, and treat them that way and sort of think about that. We should also think about, if we're going to learn something and you don't know something on a project, the hard stuff, do it up front. There's a number of really good reasons for that. Is by doing something up front, is you'll start to refine your estimates much quicker, but you'll also get much more time to go through that learning process and getting it right. When we start something new, don't do all the easy stuff that you already know the answer to. You can easily do that at the end, and you can do that under pressure when you're rushing. You want to do the hard stuff up front when you're fresh, so you get the most time to do it, and you get the ability for that to bake in and do it well, and get the time to do the second point, a point that I'm going to talk about later. But one of the other things we can do is we can also learn from online. So this whole nonsense about we get someone into a room and we get them to write on a whiteboard as part of an interview, like in our daily work, we have access to internet, we have IDEs, we have all sorts of great things. We read stuff online. Right. If I go back to the early 90s, and I remember interviews were always asking people to recall stuff, like, can you remember how to do such and such? With the advent of the internet, those people are completely redundant. The ability to recall doesn't matter anymore. What's important is, can you read on their information and tell whether it's good, tell whether it's applicable to what we want to have? That's the really, really important thing that's out there. So whenever you go onto Stack Overflow and you're going to cut and paste, the important thing is, are you cut and pasting the right thing? How do you know that it's good? How do you know that it's applicable? So let's sort of explore that topic a little bit. But first up, like, if we're going to learn, one of the most important things we need to be able to learn is time. We need the time to do that. And to get time, what we have to do is we've got to automate as much as we can. Because the hard stuff, we want the time to save for that. You don't want to be wasting your daily time on the boring, repetitive stuff. It's also error-prone, it's wrong, it's driving the wrong way. We should be investing in CI. Like, there should not be a company today that does not have CI. I know there's many that do, but it's just wrong. Like, if we're going to become engineers, we're going to do it right, we've got to have this all automated. It has to work really well. When we start learning, the most important thing to do is to focus on the feedback cycles. So when you don't know something, how do you get from not knowing to knowing more in the shortest possible path? How do we get those feedback cycles short? That's actually the fundamental of Agile. Agile is all about reducing the cycle time and the feedback cycles on stuff, so we get to find out much sooner rather than putting stuff off to the end. Focus on that thing. As we play, as we deal with stuff, we've got to experiment. If you don't know something, be very comfortable saying you don't know and create an experiment. We move forward. But as we do experiments, we should measure. We've got to measure and do things in the right sort of way and get the right sorts of answers. But whenever you do measure, one of the very important things is that we follow good scientific honesty. It's so easy for us to fit data to a certain belief system. We need to try and divorce ourselves from that. There's some great stories from Richard Feynman's work, particularly on the Space Shuttle Challenger. Whenever that happened, there's a Rogers report that came out. It's another great thing to go read if you ever get the chance. In the early days, the group that was put together, headed by Rogers to find out what happened with the Space Shuttle, had Richard Feynman on it, also had Neil Armstrong, had a bunch of other quite well-known people on it. And to begin with, Rogers wrote an interesting note saying that Feynman is a pain in the ass. He just questions everything. He doesn't accept anything. He is always going against a lot of the rest of the team. But after a while, what Rogers come to learn is he wasn't being awkward. He just realized that a lot of other people were just trying to fit an answer and trying to do it right. By the end of it, his report on Feynman was he's got the greatest scientific honesty of anyone he ever met. And that's quite a rare thing. So even if we do measure, experiment, do all the right sort of things, is we got to analyze the data, but don't fool ourselves. Like, always ask, am I actually fooling myself and trying to fit the data to the answer? Be comfortable with if it's not clear, sort of go and do it again. And probably the most important point around how we change our behavior on a day-to-day basis is this concept of revisit and refine. So we've got an interesting thing in how our brain works. We work in short-term memory and we have long-term memory. So if you go to do something, you're doing it all within your short-term memory to begin with. So take a simple example is you write an email. You write that email and you go and read the email back again straight away. You don't actually read the words of the email. You read what you think you meant to write, not what you've actually written. If you leave that, go away and come back again, so maybe another day, do another task or something, come back, because that's now gone from your short-term memory, is you have to truly reread again. And by truly rereading is you get to see what you've actually done, not what you thought you've done. This applies equally with code. It applies with anything we do that's a creative endeavor. So when we plan and do our work on a day-to-day basis, we need to be thinking about how do we plan the time so you do something, you leave it, you go do something else and you go back and you read it again and you revisit and you refine. I keep finding that I can really improve the quality of code by following that as a simple pattern. You'll also have learned more things by doing other stuff later, go back and revisit. So you think about the waterfall approach, it's actually designed to do the worst possible job you can. The iterative stuff, we need to take it much, much further. Not just that we do lots of mini waterfalls, but we actually go back and revisit and refine and do proper refactoring and also be honest with ourselves at times. Go, that's not good enough. How do I make it better? How can we go forward? I want to kind of pull out an interesting point here. So having worked with some of the NASA folks, I love one of the questions that one of the guys, Todd Montgomery, I've worked with a lot, always asks is, when you do something, he goes, what can go wrong? It's kind of a bit of a problem that they have to face in the reality of it, but it's actually really important for us. Like, I've seen working on distributed systems where so many people just assume stuff always works. You get to work with some of these people is they don't. They assume it's always going to fail. It's a completely different mindset, and they code appropriately. They code with safety in mind to do that. Here's another great report that's worth reading. It looks into production outages of code, and based upon the production outages that were investigated, it did some root cause analysis to see what some of the cases were. There was some really interesting stuff around how 70% of them could easily have been caught by a unit test. But one of the most important things I think that really stands out is 25% of production outages that they studied could have been dealt with if the error was not ignored. Real errors were raised and they were just ignored. In many of the cases, there was an exception block in code with a to-do comment in it saying, must fix this before production. That is real engineering when you don't do those sorts of things. That's when you're being very amateur, versus doing the true engineering. So it's kind of bear that in mind, that most outages after human error are actually how we handle errors. Most people just ignore them. So kind of getting close to the end now, but fundamentally, we've got this hugely complex problem. We have a war on complexity we need to fight. If we're going to have cars with 350 million lines of code or more in them, we just can't reason with that. I think we need to think much more along these lines, is think about lines of code spent. Like, you don't measure an aircraft by the weight, you measure it by what it's capable of, and you want to keep the weight down to an absolute minimum. We've got to think about how do we get lines of code down. One of my favorite measures in any given team that I'll motivate people on is lines of code deleted. Delete the dead code, delete code all the time. See if you can add features and remove code. So, kind of quickly in closing now. Whoops. It's kind of, don't feel bad. We're living in this era of software alchemy. We're like the physics of the 1600s. We gotta work this out. We gotta get better at it. We're gonna make lots of mistakes. But hopefully we're going to get better at it, probably quicker than the physicists did, because the world is so dependent on software. It's in everything we do now. So it's up to us to try and make it better. We've got to become more professional, we've got to become the engineers. And it's a really cool thing to do. Like, we work in one of the best industries there is out there. So don't create the shit. Do epic shit. And on that, thank you very much. I don't know if we have time for questions, or have we done? A couple of minutes. Do we have any questions, or are we good for breakfast?
I don't see the hands.
Yeah, I can't see a thing here.
You don't have questions for Martin? Oh, yes, maybe.
So good morning. Thank you for this very interesting talk. I just had a question. Since you mentioned this history about we need to refine, revisit all the time, back in the 70s or even before, how come waterfall happened?
Very good question. I have a personal theory. I don't know how correct it is. I think we have a large number of organizations who have put their commercial interests ahead of the interests of developing good software. I think the perfect example of that was the move to application containers, like what we've seen with like MTS from Microsoft, what we've seen with EJB and stuff from a lot of that consortium, because a lot of the vendors wanted to sell a platform and they drove a lot of that sort of stuff. It's like you can't sell very easily good design fundamentals. That's a skill that we need to work on. I think that's a craft that we need to do. And the problem is our industry is so driven by large marketing budgets, particularly through the sort of 90s and 2000 onwards, that it was driven by those corporations who wanted to have their commercial interests. They would pretend they were doing things sort of to help making good software, but in reality they didn't. I love one of the comments from the guy who was key to WebSphere, eventually admitted that it was all wrong and he shouldn't have gone that way. But it's that's what the industry's pushed, because that's how they can make money. If we could work out how to make money from good software done well, it'd be very, very different. Maybe we got to see that a lot of these things are much more long-term. We've kind of in a world where everything's incredibly short-term. We want instant gratification. So if there's not direct cause and effect, I'm a big fan of science. And if you look at the UK, in the UK, any investment we have done in science has been the greatest long-term investment ever for the country, yet we don't do enough of it because it doesn't return in the same political cycle. It's the same as like when you look at corporations who they're looking at their next quarter, their next annual return. Unless they get a good result around that, we get things just ignored or thrown away. And that's very much a thing of like the bonus-driven culture and the corporate world that drives that. So that's my theory on what it is. Who knows what the actual truth is? Okay, thank you very much.
Thank you, Martin. Really nice.